Okay. Electrical energy equations. Okay. First one, KQ1 Q2 over R. And this is if they give you information about two charges, right? So they tell you what the two charges are and the distance between them. Then you can use this equation to figure out the energy. So if you were to take a positive charge here of 6 microcoulombs and a negative charge here of 3 microcoulombs, you could figure out the electrical energy that would be required to hold those two things in that spot. Now, of course, they would be attracted, right? So if they're attracted to each other, to prevent them from moving, you would have to hold them back with a force. In other words, you'd have to apply energy. Okay? There would have to be a certain amount of energy. If they moved, they would move through a distance because of that force that's attracting them and cause the energy to change. They would do work, which is the change in energy. So just to have them sitting in this spot requires a certain amount of energy. Just like when you lift a box up on a shelf, it has a certain amount of gravitational energy to sit there. And if you move that shelf away, it'll fall. Work will be done. So if you don't hold these back with a certain force, then they will attract. Now, we can figure out what that energy is between them simply by doing K, Q1, Q2 over R squared. Sorry, over R, not squared. Ooh, don't make that mistake. It's very common. You'll make it 6 times. I just made it now after 25 years of doing this. So you got to watch. Don't make that energy R squared. It's just R. So that would be electrical energy equals 9 times 10 to the 9. 6 times 10 to the negative 6, because that's microcoulombs. And then 3 times 10 to the negative 6. You'll notice I'm not putting in a plus or a minus here. I'm going to show you why in a minute. Now, we'd have to know how far apart they were. So if they told us this and they said the distance between them is 0.2 meters, then we would put that here, 0.2, and it's just plug away and play, right? So I'll get out my calculator here, and be careful with your exponents. There's lots of scientific notation. 9 times 10 to the 9 times 6 times 10 to the negative 6 multiplied by 3 times 10 to the negative 6 equals, divided by 0.2 equals 0.81 joules of energy. That's the amount of energy that has been put into these things to get them to this position. All right? You can imagine if they were both touching, if they were both together, and somebody had to stretch them apart against their attraction, they would have to put in 0.81 joules of energy to stretch them apart to 0.2 meters. So that's how we can use that equation. And we use it when we have information about both charges and the distance between them. Okay. Now, I could rearrange this. Instead of telling you about two charges, what I could do is I could say, there's another charge over here somewhere, right? But I'm not going to tell you what it is. Instead of telling you the charge, I'm going to tell you that it creates a field. Okay? And in fact, I think I can still do it with a point charge. Well, we'll try it. In fact, what I'm going to do is do it in blue. It creates this field. So all around this charge is a field. Like this. You can tell what kind of charge that is now by looking at those arrows. You know whether that's a positive or negative charge because the arrows always go away from a positive charge, which means this is a positive in here. So even without the question telling you, the arrows tell you there's a field. Okay? And it's if that's the field, then that's a positive charge. And I'm going to tell you that at a particular spot right here, which happens to be 0.2 meters away, there is a voltage. I'm going to say that the voltage at that spot equals 6 volts. Okay? So that means that there is 6 volts, or 6 joules of energy for every coulomb of charge you try to push there. All right. So now I might say, well, determine the master charge. What is it? What is the charge here? We know it's positive, but how many coulombs must it be? Well, we can go back to our voltage equation, right? And remember that voltage around a certain distance away from a point charge would be V equals K Q, the master charge, over R. So 9 times 10 to the 9. Well, actually, let me do it. I'll go down a line. We'll go down here. The voltage in this case is given, so 6 volts equals 9 times 10 to the 9 times QM, and it's 0.2 meters away. It's 0.2 meters out in the field, so 0.2. And you crunch this out, you're going to get a number. Now, this is going to be a gigantic number. And the reason for that is because we typically don't get voltages of 6 with point charges. I just pulled these numbers out of the air to show you. Typically, we get very tiny charges, but it is possible. It's just very weird. So 6 times 0.2 equals, and then divided by 9 times 10 to the 9 equals, well, actually it came out pretty good. It comes out to 1.3 times 10 to the negative 10 coulombs of charge. So that's actually about 0.1 nanocoulombs. It's a very small amount of charge. So we used this equation because now we weren't talking about 2 individual charges. In other words, we only knew information about one charge in this case. Now, it doesn't matter whether it's the master charge or the other one, but in this case, we were looking at one charge only. They were asking for the charge, determine the master charge, and there was no information given about this other charge over here, the QT. Nothing. We knew nothing about it. So we know that we can't use this equation because we don't know enough. But the voltage equation can be used because it only deals with the master charge and the distance. And so there's a situation where we could have used the voltage equation, right? All right. Let's do another example. How much work is done in moving a 2 microcoulomb charge a distance of 0.6 meters in a field, an electric field, with a field strength of 10 newtons per coulomb. Okay, what does this mean? Well, it means there's a field. We'll just draw it this way. There's the field, E equals 10 newtons per coulomb. And we have an object in here, and we want to move it. How much work is done? All right. So now, which way are we going to move it? Well, we're going to assume we're moving it against the field, because otherwise, why would we be doing any work? Work is done, and this is the catch that people don't understand. If I take this object right here, and I allow it to go this way, then the work is done by the field. The field does the work. No additional force is necessary. But if I want to move this object against the field, if I want to take an object here and push it this way, then I would have to do some work on it, okay? So how much work do we want to find, or do we want to do here? Okay, well, our work equation comes from work equals, it's a constant field of 10 newtons per coulomb. So work equals QED, constant electric field of 10. So what we're going to do is find out how much work is done by saying, well, we're going to take this charge of 2 microcoulombs, so 2 times 10 to the negative 6, and we're going to push it through the field, which is 10 newtons per coulomb, a distance of 0.6 meters. So you can see that it's not so bad. It helps to just write down what you've got and then find the equation that would work, right? So that's going to be 10 times 0.6, which is just 6, right? Times 2 to the exp negative 6. And that means that the work done is 1.2 times 10 to the negative 5 joules. All right, so there's where we would use that equation if you have a constant electric field. And some of the questions will be set up, or they'll tell you that that's the case. Okay, so you essentially have three basic formulas that we're going to work with now. We won't worry about the parallel plates one just yet. Let's just work with these three formulas. E, K, Q1, Q2 over R squared. Over R, rats. That's twice I did it. Not R squared. Over R. Don't make that mistake. And if you have information about both charges, you do this. Okay? You can also look at the work done. Energy is also work, right? So we can look at work or electrical energy change. That could be the change in electrical energy. And that's when you have QED. But remember, constant E. So if you only have information about one charge, then perhaps this is the one that you can use. Then we have this concept of voltage, which is energy divided by charge. So we can use this equation, energy divided by charge, to figure out voltages. And if we apply that equation to certain situations, right, then we got the shortcut formula. This would be the energy at any given point. But if we specifically wanted to look at voltage around a object making a field, the master charge, it turns into this, KQM over R. And those are basically the four formulas that we're going to mess with right now. Okay, now there is one more thing in the next video, and that will be how we can use electrical energy in energy conservation situations. If you recall, we were able to do last year EK and EG, remember? EK1, EG1 equals EK2, EG2. Well, now we have this other thing, EE, which is another form of energy which can go into these conservation equations. And we're going to learn how to do that in the next video. But for now, practice